Now, in this video, I'll be talking about another important detector and counter, what we call as GM counter. And this GM counter, it stands for Geiger Muller counter, and it's a count rate meter, and which was first used in 1908 by Rutherford and Geiger, to evaluate the charge carried by alpha particles. And it was improved later on in 1928 by Geiger and Mueller in Germany. So it's a special form of ionization chamber operating at considerably higher voltages of the order of 800 volts to 1500 volts. That's it works in Geiger region that we'll be talking about, the region that we have plotted already, the fifth part of that region. Now let's go with let me have a simple schematic diagram to illustrate the things down here. What I have is something like this, and in here I'll go here. Then I have a resistor, and here we have a capacitor, and this is R, and this is R dash, and then we can have a capacitor, and then we will have a counter, and this all should be connected, and and we can ground it here like this, and then we'll have a battery, and this has to be positive. So the wire that we have, that has to act as anode, and and the cylinder will have negative charge of the battery. Okay, so here we are using nearly 800 to 1500 volts of potential difference. We can ground it, and what we do is we allow the radiation to go into the chamber. So let's talk about it. What we have, these GM tubes. These tubes have been made in great variety of sizes and shapes all around the globe, from 1 centimeter to 100 centimeters in length, and from 0.3 centimeters to 10 centimeters of diameter. The walls can be of metal, copper, and a metallic cylinder may be supported inside a glass tube. So we can have, I should quote this as a glass tube. So my connections should go inside so that I can differentiate. This is my metallic cylinder, and this should be an insulator. There should be some insulation. So so to move further on, what we have is that this metallic cylinder that we have, it is supported by a glass envelope, or the interior surface of this glass tube may be coated with some thin layers of an electrical conductor. For example, we can have a silver paint from inside of this glass, and the central wire that we have, this central wire is usually made of tungsten. Same was the case with proportional counter, and its thickness can vary from 2 times 10 to the power of minus 3 to 5 times 10 to the power of minus 3 centimeters. And the wall thickness of the tube is governed by the nature of the particles to be detected. So a thickness corresponding to nearly, if I assume 300 milligrams per centimeter square of wall area, it readily passes the gamma rays, but it blocks alpha and beta particles. And with the glass walls of say 30 milligram per centimeter square, all the gamma rays and most of the beta particles are transmitted with this thickness, but alpha particles are blocked. So in this case, with this thickness, so there has to have a different range of, depending on the types of the particles that have to be detected by the counter. The thickness of the walls is selected in accordance with that. Now, what we have here is a high resistance R. It is connected in series between the uh, actual anode and the cathode. So this is the cathode and this is the anode. All right. Now, the potential difference that develops at the end of R, here we will have the potential difference. It is sent to the counter through a circuit containing a condenser. And a resistance R dash. And the condenser, what it does is it obstructs the DC components of the potential developed across this R in going to the counter. Now, since the potential difference across the electrodes correspond to the region 5 that we have talked about, and even a minimum ionizing particle that goes inside produces a large ionization pulse because of Townsend avalanche that we talked about. And the main difference between the proportional counter and GM counter is that in case of proportional counter, what we have had was the avalanche was available. The avalanche could develop only at the point of the wire. The avalanche could be developed, but in case of GM counter, what happens? The avalanche spreads along the whole length of this wire. It spreads along the whole length of this central wire, and the amplification does not therefore depend on the initial ionization that was produced by the ionizing particles. Now, after the avalanche, the electrons, being very light particles, they get collected. They get collected at the anode in a very short span of time, of the order of 10 to the power of minus 6 seconds, and leave behind the positive sheath of charge, sheath of ions, which drift slowly, they move slowly towards the cathode. Now, the counter comes back in its original state after all the charge. After all the charges have been, so the case over here is that since electrons being lighter particles, they reach this anode in a very short span of time. But instead of talking about the ions that we have, the ions, they make a sheath of charges. They take longer to reach the cathode. Now, when the particle enters this active region of the counter and produces few primary ion pairs inside the tube, a large number of secondary electrons are produced here, and which leak through some external circuit resistance R that we have. Now, a fast rising pulse that we have for the time TR, nearly equal to 5 times 10 to the power of minus 7 seconds. It appears across this resistance. And a positive ion sheath that goes very slowly with respect to the motion of the electrons. What it does is it develops thereafter and makes the counter dead. And the positive ions are quenched without any radiative transition by filling the counter by some organic or halogen gas with large molecular size, which helps to deionization of the positive ions, and the counter recovers to its original voltage condition quickly in a very short span of time. So the quenching process, in quenching these tubes, what we have, we use 90% of argon and uh, and 10% of ethyl alcohol. Ethyl alcohol, and and that too at a pressure of nearly 1 to 20 centimeters of Hg. The time for which this counter is dead, we call that time as dead time. So we have the time that's called dead time, and let us assume that this dead time is Td. It's the dead time, and the counter recovers, and there is a recovery of the counter, and let's suppose that time is Tr. This is the recovery time of the counter. It's the time after which the original pulse level is restored, and the usual resolving time for this GM counter is equal to the sum of this dead time and the recovery time. So when we add up these two times, that gives us the resolving time of this GM counter. And so what is my resolving time? My resolving time is simply Td plus Tr. Now, talking about a plateau, if I plot the characteristics, if I choose this as applied voltage, the range of this voltage is already given, and here if I have pulse height, and what we obtain is something like this. Let me draw it and have discussion on it, and then it goes like this, and this I will call as I will call this as A, and I'll take some middle point as C, and this is my point B. All right, now this A to B region that we have, this is the working region. Now the variation of the pulse height as a function of this applied voltage can be seen, is over here, and we can see a plateau curve of GM counter. Now if the height of the pulse is less than that corresponding to this point A, the pulses are passed by the electronic discriminator circuit of the GM counter that we talked about. Now the discrimination level of the GM counter, counting the circuit, is adjusted in such a way that it counts only those pulses whose height is above this threshold limit A of this plateau curve AB. And they happen to have the counters who are considered to be superior if its plateau is longer and flatter with the minimum slope in AB, and the counter and the organic quenching that's being executed on the GM tubes must have longer plateau with smaller slope as compared to the halogen quenched tubes. Now these GM tubes are operated at a voltage corresponding to this middle point that I have tried to show here as C, as C of the plateau. Now, talking about the resolving time, if I assume that counting a system with a resolving time with the resolving time. Say tau. What is this tau? It's the respond rate. With the respond rate equal to n counts per unit time. Per unit time when exposed to n initiating events per unit time. Now, so what I have is I have tau, I have a respond rate that is small n, and I have the initiating events. These initiating events are capital N and N. That's the case. Now, in unit time, the total insensitive time will simply be n tau. So, insensitive time, when there is no respond from the counter, that will be n tau. And the number of counts missed, that must be n and tau. So we can write down mathematically that the number of missed counts must be equal to simply error in counting. It should be error in counting. So how much I have missed counts, that's n and tau, that must be equal to the error. That error must be n minus n. So we can have n and tau minus n is equal to minus n. So we can have n times n tau minus 1 equals minus n. So this n can be minus n by n tau minus 1. So this is n by 1 minus n tau. So this equation is going to give me the actual count rate of the GM counter. And thus, the actual count rate can be calculated by knowing this tau. And what's that tau? This tau is the resolving time. So with this, I would like to stop here. Have a nice time. Bye.